Welcome to Maths with EJD. I did this numerical analysis playlist about 8 months ago, but then, one of my viewers saw a video on least squares approximation for overdetermined equations, and he feels that there is need to do the one for underdetermined equations. And I'm gladly obliging. Thank you for coming to my channel and for asking for this. I'm very glad to make the video for sure. So for some weird reason, I didn't think of making a video for underdetermined equations the last time. So here we are. All right. So we're talking about least squares approximation for underdetermined systems. An underdetermined system of linear equations is one in which the number of equations is less than the number of unknowns. So you have number of equations less than number of unknowns, and that is said to be underdetermined. Okay, so it's underdetermined, underdetermined. Okay, underdetermined if number of equations is less than number of unknowns. Okay. So the overdetermined case is when you have more unknowns than equations, right? So we've taken that case. That's the 34th video in this playlist. So a very simple example of this will be something like this. You have x1 plus x2 equals 3. Okay, that's all you have. So here you have one equation, and then two unknowns. So you have one equation, x1 plus x2 equals 3, and you have two unknowns, x1 and x2. So the usual solution you get in this case is infinitely many solutions. You get infinitely many solutions. Okay? So because the best thing you can do to this is to have like x1 equals 3 minus x2. Okay? So you can get for different values of x2, you can get your x1, right? So if you say that, or better still, you can also say x2 equals 3 minus x1, anyhow you want to have it. So, so you're going to get infinitely many solutions. So imagine if you have your x1s and then for x2 now. So if x1 is 0, of course, x2 will be 3. If x1 is 1, x2 would be, if x1 is 1, x2 would be 2. If x1 is 2, x2 would be 1. Okay, all right. If x1 is 3, then x2 would be 0. Then if x1 is 4, x2 will be minus 1. And then it goes on and on like that. So that's why for underdetermined systems, you have infinitely many solutions. But then, because it has infinitely many solutions, that is where this whole idea of least square methods comes in. So least square methods now helps you to find the least of those infinitely many solutions. That's what least square helps you to take care of. So an undetermined system of linear equations is one in which the number of equations is less than the number of unknowns. So for a system, ax equals b, all right, where A is an m by n matrix, for x belonging to the n-dimensional real number system, and b is an m dimension. B belongs to the m-dimensional real number system. The system is underdetermined when m is less than n. M less than n simply means that you have fewer equations than you have variables. That's basically what that is telling you about. So you have more variables than you have equations. So such systems usually have infinitely many solutions or no exact solution, just like what I demonstrated. So, when the number of equations is equal to the number of variables, so you can have exact solutions, right? But here, you have infinitely many solutions. So the least squares approximation helps us find the best possible solution by minimizing the error between the predicted and observed data. That's what least square does for us. So let's talk about the least square principle again. So the goal of the least square principle is to find a vector x that minimizes the residual norm. So you're looking for the minimum value of x such that the absolute value of ax minus b the norm, norm of ax minus b, right, is minimized, right? So this is known as the least squares problem, basically. So for overdetermined systems, which we had done in video 35, m is greater than n. This gives the best fit when no exact solutions exist. Okay, so you have m greater than n. That's more equations than you have variables, which was done in video 35. Okay, so the least squares method gives best fit when no solution exists, which I did in that 34th video. So for underdetermined systems, which we are considering now, m is less than n. So the least squares approach can also be used, but it must choose among infinitely many possible solutions. So in this case now, there are several solutions. So what the least squares method helps you to do is to pick one among the infinitely many possible solutions. Okay. Now that takes us to the concept of normal equations and general solution. So the normal equation is A transpose AX equals A transpose B, right? So of course, we started out with AX equals B. So the normal equation for this will just be A transpose. We started with AX B. So you now multiply both sides by the transpose of it. So A transpose A equals A transpose B. That's how you start. All right, so take the transpose. So where A has linearly independent rows, so A transpose A is singular since A has more columns than rows. All right. So when we talk about the idea of when something is singular, it means that the determinant is 0, right? And then you cannot find the inverse of that. That's a challenge on its own. So when A has linearly independent rows, A transpose A is singular since A has more columns than rows. Therefore, we use the more Penrose pseudo-inverse denoted by A plus. So the minimum norm least square solution will now be x equals A plus B, where so beyond taking the inverse of this side now, we now go ahead to look for A plus, which is, A transpose, AA transpose. So the inverse of AA transpose like this. So it's, for the other case now, I think all we just needed to do was A transpose A on both sides, A transpose on both sides. But here we have to go further because we get a singular matrix from A transpose A. So we now do this minimum norm least square solution using the more Penrose pseudo inverse, which says that A transpose into A transpose inverse like that. So we are going to take an example, of course, of that as we move on. So among the infinitely many x satisfying ax equals b, or nearly so, all right, the minimum norm solution chooses the one with the smallest Euclidean norm. That's the norm x, to 2. So this ensures stability and physical interpretability, particularly in applications like signal reconstruction, control systems, data fitting with limited measurements. So imagine this example here. Of course, it's already solved there, so I'm going to go to the next page and also still do that. Okay. So this is basically saying that we have 101. A is 101, 011, and B is 12. Okay, so let's go to the page where we can do some work. Okay, so imagine, of course, if you want to write this out, right, that's about saying that you have um you have something like this. So you have more equations than you have variables, right? So here now you have 2 equations and 2 variables. Okay. I mean, you have 3 equations and only 1 variable. So that's like A is 101, 011, and then B is 12. And of course, this is where we must be coming from. So you have A to be, so AX equals B will simply imply that you have 101, 011, okay, into B. I mean, X now. So our X is simply X1, X2. So you have 2 variables. What are we saying here? You have less equation than you have variables. Okay, yeah, I think that is it. So this will have to be X1, X2, X3, X1, X2, X3, okay, equals 1, 2, like that. So, and of course, the way I explained matrix the other time, for you to have this now, this will have to go with this. And of course, this will have to go with it again. So then we can have x1, x2, x3, right? Just write it twice, x1, x2, x3. So, and then invert the first one on it. So 101 comes in 101. And here, you have 011. Okay. And all this now is equal to 1, 2, basically. So in this case now, you basically just have, so that means you have x1 plus x3, okay, equals 1. That's the first equation. And the second equation will be x2 plus x3 equals 2. So here now, so uh, so you see the variables, we have the variables, 3 variables, x1, x2, and x3 in all. Then equations, we have equations 1 and 2. Okay. So this is over-determined. I mean, this is underdetermined because you have more equations. I mean, you have less equation than you have variables. Okay, you have just 2 equations. So in that case now if you want to use the approach I just demonstrated over there, so the first thing we want to do is to find, so first thing, because ultimately we need the pseudo inverse, the more Penrose pseudo inverse, which is A transpose into AA transpose inverse of this now. So we need this ultimately because that's what gets us to where we are going to. Okay, so once we get this now, we know our x is going to be that a plus b. So this will give us the value of x. So our first job is to get this AA transpose. Okay, so we need AA transpose. So we know A is 1, 0, 1, 0, 1, 1. And the transpose of this will simply be, so transpose means turn row to column and column to row. So first row, 101 becomes first column, 101. Second row becomes second column, that is 011, like this. And that is equal to, this is more like, so that AA transpose now, we need to find it. So, and how do we get this? So you just follow what I've done just now, and this will simply be equal to, so because you have 2 rows here, so you have to write each one twice, right? So you have 101, 101, okay? So, and that will go with 101, 101, okay? And then you also have the other one, 0, this 011 now. So this is the first, this is the second, 011, 011, okay? And then for this is the first row. So that 101 comes over, it's 101. And then this 101 also comes over here, 101. And then for the second one, okay, so that's the second one. So you have 011 and then 011. Okay. So with this in place now, we can tidy things up and then we have this. So of course you multiply and add, right? 1 times 1 is 1, 0 times 0 is 0. So this is 1 plus 1, and you just have 2 here. This is 0, 0, you have 1 here. This is 0, 0, and you just have 1 here. This is 0, 1 times 1, 1, 1 times 1, 1. You have 2 here. Okay? So we see now that A transpose, then, AA transpose is equal to, AA transpose is equal to 2, 1, 1, 2. So we find that that's the first step from what we have here. So that's the first step. Now, after that first step, the next thing we want to do is to find that the inverse of that. Okay? We want to find the inverse of this one. And so that means we just come and say, we now need the AA transpose, and then we find the inverse. So of course we know we not find the inverse of this. That means we are looking for the adjoint of AA transpose all over the determinant of AA transpose. That's what that simply means. And the adjoint is easy. So the adjoint, for a 2 by 2 matrix, it's very easy. All you just need to do is, all right, you keep these values the way they are. Okay, you keep these values the way they are, and then you switch these ones over and change their signs. Okay, so I mean, if you follow the regular determinant thing, so up there now we have 2. This is -1. This is -1, and this is 2. All over the determinant. The determinant, of course, is the absolute value of 2 times 2, 4. So you have 4 minus 1. Okay, so that means that A transpose inverse is equal to 2 minus 1 minus 1 2. Okay, all over absolute value of 4 minus 1. That's okay. I don't think it's absolute value actually. So just simply 4 minus 1. So that's 3. Okay, that means we have that to be 1 over 3 into 2 minus 1 minus 1 2. Basically, okay, that's the inverse. So another step completed. So we have done we are done with this part now. So the next thing is we now multiply this one with A transpose again, right? So we have A transpose in front. So we can move on with that. So we can say, so now we have A plus, which is A transpose inverse. Okay, so that means that A plus is equal to A transpose, like we did before, is 1 0 0 1 1 1 into what we have found. That's into 1 times 3 into 1 times 3 into 2 minus 1 minus 1 2. Okay, so the 1 over 3 can come out now. So A plus is 1 over 3 into 1 0 0 1 1 1 into 2 minus 1 minus 1 2. Okay, excuse me. So A plus is 1 over 3 into, so now we can do what I like to do. So you see this one is in 3 rows now. Okay, so you have this one in 3 rows and this one is 2 columns. So it means you are going to write each column 3 times. Like if you want to follow my style, you write each column 3 times. So you have 2 minus 1, 2 minus 1, 2 minus 1. And then on the other hand too, you have minus 1, 2, minus 1, 2, minus 1, 2. Okay? And then for the first one now, you have, say, this 1 0. So you have 1 0 and 1 0. Then for the second one, you have 0 1. So that's 0 1 0 1. Okay, and for the last one, that's 1 1. So you have 1 1 1 1. So you multiply and add again, like we've always done. So you have A plus to be equal to 1 over 3 into, so here we have a 3 by 2 matrix. So what is that? 2, this is 2 and plus 0, this is simply 2 here. Then up there we have minus 1 times 1. That's minus, okay. What do we have there? 1 over 3. Okay, minus 1 times 1 is simply minus 1 up there. Then I guess this has to go. Then the next one, minus 2 0. So this is also minus 1. Then next, minus 0, this is simply 2. And here 2 minus 1, that is simply 1. And here minus 1 plus 2, that's also 1, like that. So now this is what we have. Okay, so this is A plus, which is 1 over 3, 2 minus 1, minus 1 2 1. So like I said the other time, don't forget where we are going to. Now we have found the whole of A plus. So what do we do next? Our next level is to find X, which we are actually looking for using least square method. That's that A plus now multiplied by B. Don't forget our B is this 1 1 2. Okay, our B is this 1 2, like that. So we now do, finally we find that. So you can say finally, okay, finally X is equal to A plus multiplied by B. So what is A plus? We do that. So X is A plus. A plus is 1 over 3 into 2 minus 1, minus 1, 2, and then 1, 1. All right, multiplied by B. B is 1, 2. Of course, you see this is 3 columns, and this is just 1 row. So you're going to write this 1, 2. You're going to write it 3 times, okay? you write it 3 times because you have 3 rows on the first matrix. So you write this second one 3 times. So let's go carefully. So X now, you have 1, 3, of course, is out there. Then you have 1, 2, 1, 2, 1, 2. Okay. So for the first one, you have 2 minus 1. That's this one. The second one, you have minus 1, 2, minus 1, 2. And last one, you have 1, 1. Okay. So you can say now that X is equal to 1 over 3 into 1 times 2, 2. 2 minus 1, 2 times minus 1, 2. So 2 minus 2, that's 0. Then this is 1 times minus 1, that's minus 1. 2 times 2, 4. 4 minus 1, that's 3. 1 times 1, 1. 2 times 1, 2. That's 3 again. So lastly, you have that X, if you divide through by 3, so you have 0 over 3. Okay, you have 0 over 3, 3 over 3, 3 over 3. Okay, so finally, X is equal to 0, 1, 1. So that's what we have got using the least squares method. So, of course, there are several solutions to this problem, but this is probably the least of the problems. So, X now is 0, 1, 1. So, you can say X is the same thing as 0, 1, 1 transpose, because this is the transpose of this, right? So, I mean, if you investigate the problem on its own, so if you investigate the problem normally, this is the original problem, right? Where is it now? When we write out the equation, so if you investigate this just the way it is, so you see x plus 1, x plus 3. So first of all, okay, what can we even do? We can eliminate. So, I mean, if we find a way of fixing everything up, it's not even possible like that, because I mean, so let's start from instance, if x1 is 0, okay? If x1 is 0, okay, that means if we fix x1 to be 0, that automatically means that x2 would be x2, sorry, so we can get x3, right? So if x1 is 0 here, x3 will be 1, okay? And then, and once you know x3, right? X3, so once you know x3, it means that you have x3 is 1. So it means x2 will be 2 minus 1, and that will be 1. And that is the solution we got there. So that's one of the infinitely many solutions. So the next thing is you can go for x1 is 1. If x1 is 1, for instance, then automatically x3 will be 0, okay? And then now that x3 is 0, it means that x2 is 2. So you see infinitely many solutions. If x1 is 2, okay? If x1 is 2, that means that x3, all right, x3 would be 1 minus 2. That's minus 1. And since x3 is minus 1, all right, so that means that x2 will be 2 plus 1, 3. So you see, you have infinitely many solutions, but of the infinitely many solutions, this is the smallest of them all. And that is what least squares does for you in this situation, okay? That's what least square does for you here. So let's go back to that page. Okay, so now you see we have solved this manually over there. So I also have Python implementation of this to drive the point home. So for the Python implementation, all we just do is we import NumPy as NP, define the system. So if you write in, I mean, you can easily use Google Colab to write this out. So just open, if you have a Gmail account, just open Google Colab and open a code page, and just copy and just write this code and you get the result. So here now define the system. A, numpy array, that's 101, 011. B, np.array, that's why we need numpy, right? Numpy works with arrays, and this is 1, 2. Then you compute the pseudo inverse and least square solution. So here now you have x now to be np.linalg plus p inverse. P inverse is the pseudo inverse of A now. So all that lengthy thing we did, all the maths we did to get to A plus, which is A transpose into A transpose inverse, that's what this line is doing for you. And then at B, this is multiplying with B, basically. And then you print least square solution, and that gives you the minimum norm. So since you have infinitely many solutions for that kind of system, then you get the least of them all. So you see now this is 2.22 times 10 raised by minus 6. That's like 0.0000. That's like 15 zeros before you get to 2.2. That's roughly 0. That's what we got at 0. And these other ones are 1. So you have 0, 1, 1 like we got. So the code just gives you that pretty easily. Okay. Then we talk about the geometric interpretation. So the solution lies in the column space of A, while the residual vector. So the solution, right? So you know there are infinitely many solutions. So those infinitely many solutions lies in the column space of A, while the residual vector lies in the orthogonal complement of the column space. So in underdetermined systems, infinitely many solutions lie on a hyperplane. Okay. So but the least squares method selects the point that is closest to the origin. And that is what this code is doing for us. So you can, go through this code and see what it looks like. Let me not take time in explaining. But I mean, if you want to have access to the code, you can see it. I'm not able to copy and paste code into on YouTube. So you can check, just type my full name on Facebook, you'll find the code there. So you can copy it into Google Colab and run. So this is what this simply means. So you see the solution line is this blue line now, AX equals B. You have the solution line here. Then you have the orthogonal segment like this. So the minimum norm is this value right here. So it's somewhere along the line, right? So this is the minimum norm. So the origin is this yellow dot, while the minimum norm x of x is this blue dot. So this is the orthogonal segment to the hyperplane like that. So this is the geometrical interpretation of what you have done. In summary, we see that if you're talking about the type of system, overdetermined, the condition for overdetermined is that you have more equations than you have variables, right? Yeah, you have more equations than you have variables, and the solution type is best fit, and the formula is x equals A transpose A inverse multiply by A transpose multiply by B. Then you get the best fit using least squares method. But for underdetermined, where you have more less equations than you have variables, right? So the solution type is minimum norm because you have infinitely many solutions. You have infinitely many solutions. So for these infinitely many solutions, you pick the least of them all, and then you can see the A transpose comes first here. And then instead of having, so everything is reversed here. So instead of having A transpose coming last, it comes first. Instead of having A transpose 8, it is A transpose. Then you take the inverse of that, multiply by B, and you get the minimum norm. All right. So, I mean, with that, you can actually take care of these practice questions. You can define an underdetermined system and explain when it occurs. Of course, we said an underdetermined system is where you have more variables than you have equations. Okay. So, what is the goal of least squares approximation in underdetermined systems? Of course, that's to help you get, since the solution to an underdetermined system is infinitely many, so the least squares approach helps you to get the minimum norm. That's the smallest of all the solutions, and then you can try the rest of this. So with this, I come to the end of this video. Once again, thank you so much. Let me see if I can find the name of the person that made this request. Thank you for for checking out this my videos on this channel. I do not take it for granted. I interact with this at all. I think you deserve to be mentioned. Let me look for the name. Trying to look for the name now. Let me see. Let me see. I shouldn't have taken me this month. Yeah, that's Kiza Ariel. Kiza Ariel. Thank you for this request, Kiza Ariel. Thank you for making me do this video. I wonder why I did not do it in the first place, but that's why I like this feedback. Kiza Ariel. Thank you so much. All right, so thank you so much. This is the end of this video. Let me know how helpful this is for you. And if there's something else you'd like me to do, feel free to let me know. So if you have not subscribed already, of course, you want to go ahead and subscribe right away and hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can take it to the next level. You can become a member of this channel by clicking on join, which gives you some special privileges. All right, it gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.